Hello there, and welcome to Sleepy Science Vault. High up in the mountains, where the air is thin and cold and the world feels far away, something begins. A trickle of water emerges from between stones. Snowmelt seeps through frozen ground and finds a crack, a path, the smallest opening. Rainwater pools on a hilltop and quietly starts to move. These are the beginnings of rivers, not dramatic, not sudden, but patient and inevitable. Every river has a source. Usually it sits in high land, on a hillside or a mountain slope, somewhere elevated enough that water has nowhere to go but down. Gravity, that most constant of forces, does the rest. From the moment a drop of water touches the earth, it is already part of something larger. Water falls as rain, settles into soil, collects on rock faces, and eventually finds its way into a stream. That stream feeds into another. And slowly, quietly, a river is born. This is the water cycle at work, an ancient, unending loop that connects the clouds above to the valleys far below. What makes rivers so remarkable is not just where they begin, but how far their reach extends. A river basin can cover an enormous area of land. It gathers water from hillsides, forests, wetlands, and fields, channeling it all through a web of smaller streams and tributaries that eventually merge into one moving body. These drainage systems are nature's own networks, efficient and elegant, shaped over millions of years. And as a river travels, it changes. In its early stages, near the source, it is often narrow and fast. But as smaller streams join it along the way, it grows. It widens. It deepens. What began as a thin ribbon of water in the highlands becomes something far more powerful by the time it reaches the lowlands. Geographers describe this journey using the idea of a long profile, the gradual change in a river's slope from beginning to end. Near the source, rivers tend to be steep. The water rushes and tumbles over rocks. But as the land flattens toward the mouth, the slope gentles. The water slows. The river spreads. This long journey can be broken into stages, each with its own character, its own pace, its own set of landscapes. In the upper course, where the land is high and the gradient is steep, the dominant force is erosion. The river carves into the rock beneath it, cutting downward with surprising power. Valleys here are often narrow and deep, shaped like the letter V, worn away over thousands of years by the weight and movement of water. Further along, in the middle course, the river begins to find its rhythm. It still erodes, but now it also deposits, dropping some of the material it has been carrying. The valley widens. The water begins to curve and meander. And in the lower course, near the mouth, deposition takes over entirely. The river is slow and heavy with sediment. It builds rather than cuts. It creates rather than destroys. Floodplains spread out on either side, fertile and flat, shaped by centuries of flooding and settling. What determines how dramatically a river shapes its landscape? Three things, above all: its velocity, its volume, and the nature of the land it crosses. A fast river in hard rock will carve differently than a slow river moving through soft clay. A river carrying a large volume of water will behave differently from one that only runs full after heavy rain. Every river is a product of its environment. And in turn, every environment is, in some way, shaped by its river. It is one of the most fundamental relationships in the natural world, water and land, each constantly reshaping the other, over timescales so vast they are almost impossible to imagine. And yet it all begins in that quiet, unremarkable moment, high on a hillside, where a few drops of water find a path and begin to move. Water, at first glance, seems like the gentlest thing in the world. It yields to your hand. It flows around obstacles. It settles quietly into whatever shape contains it. And yet, given enough time, water is one of the most powerful forces of transformation the earth has ever known. Rivers erase mountains. They carve canyons hundreds of meters deep. They reduce solid rock to fine sand and carry it thousands of kilometers away. The process is slow by human standards, but by the standards of the earth, it is constant, relentless, and utterly unstoppable. This is the story of river erosion, and it begins with something surprisingly simple: movement. When a river flows, it does not merely pass over the land. It works on it. Every second that water moves across rock and soil, it is doing something. Wearing, scraping, dissolving, pulling. The river is not just a channel for water, it is a tool, endlessly grinding away at the surface of the earth. And it does this through several distinct processes, each one working in its own way, each one contributing to the slow reshaping of the landscape. The first of these is hydraulic action. This is perhaps the most direct form of erosion, the sheer physical force of moving water pressing against the riverbed and banks. In fast-flowing sections of a river, water is forced at high pressure into cracks in the rock. Air becomes trapped in those cracks and compressed. When the pressure releases, the effect is almost like a tiny explosion. Fragments of rock are loosened and broken away over time. No tools, no chemicals. Just the force of water, repeated endlessly, until the rock gives way. Then there is abrasion. As a river flows, it carries with it material it has already eroded, grains of sand, pebbles, sometimes large rocks. These particles are not passengers. They are weapons. As the current drags them along, they scrape and grind against the riverbed and the banks on either side, wearing the rock surface down the way sandpaper wears down wood. Over years, over centuries, this constant abrasion can smooth hard stone, deepen channels, and carve curved hollows into the sides of valleys. The river uses the land itself as a grinding tool against the land. Attrition works differently, though it is part of the same story. When rocks and pebbles are carried along by a river, they do not simply scrape against the bed, they also collide with each other. They knock and grind together as the current moves them, and with each collision, they become a little smaller, a little smoother, a little more rounded. The sharp boulder that fell into a mountain stream might, after traveling many kilometers downstream, arrive at the lower course as a smooth, palm-sized stone. The river has not just moved it, it has reshaped it entirely. And then there is solution, the quietest of all these processes. Certain types of rock, particularly limestone, are slightly soluble in the weak acids that rainwater naturally contains. As river water flows over these rocks, it slowly dissolves them, carrying the minerals away in chemical form, invisible to the eye, but genuinely removing material from the landscape. No scraping, no grinding. Just chemistry, working silently beneath the surface of the water. Together, these four processes, hydraulic action, abrasion, attrition, and solution, give rivers their extraordinary power to reshape the land. They do not work in isolation. In any given river, at any given moment, some or all of these processes may be happening at once, each contributing its part to the larger work of erosion. But erosion is only part of what a river does. Once it has broken material loose from the land, it must do something with it. And so rivers also transport, carrying weathered material from one place to another, sometimes for extraordinary distances. Grains of rock eroded from a mountain in the highlands may eventually come to rest in a delta at the sea, hundreds or even thousands of kilometers away. The river is not just a sculptor. It is also a conveyor, moving the raw material of landscapes from one part of the world to another. The speed at which a river flows has an enormous influence on how much erosive work it can do. Fast-flowing water carries far more energy than slow water, and it is that energy which drives erosion. In steep, high sections of a river, near the source, where the gradient is sharp, water rushes quickly, and the erosive power is at its greatest. This is where the river cuts most aggressively into the landscape. In these steep areas, the dominant process is vertical erosion, the river cutting downward rather than sideways. It deepens its own channel, grinding into the rock below it with the sediment it carries. The result, over long periods of time, is a valley that is deep and narrow, with steep sides dropping sharply to the water below. A river valley formed mainly by downcutting has a very particular character. It is incised into the landscape, almost as if something has drawn a blade through the earth and pulled the two sides apart just slightly. This is distinct from the wider, flatter valleys that form in a river's later stages, where lateral erosion, the wearing away of the sides rather than the base, becomes more significant. But near the source, it is depth that the river carves. It drives downward, pulling the valley floor lower with each passing century. The type of rock a river flows over makes an enormous difference to how this all plays out. Hard, resistant rocks like granite or quartzite do not give way easily. A river crossing such terrain will erode slowly, and the landscape it creates will be rugged and dramatic, steep gorges, waterfalls where resistant rock forms a sudden edge, narrow valleys that take an enormously long time to deepen. Soft rocks, by contrast, clays, sandstones, certain sedimentary formations, yield much more readily to the river's work. Valleys here can be broader, gentler, shaped more quickly. This is why no two river valleys look quite the same. The rock beneath makes every river's erosive story unique. And rivers are also, in a very real sense, opportunists. They follow the path of least resistance through the landscape. Where the rock is weaker, where a fault line offers a crack, where softer geology creates a natural low point, the river will find it and follow it. Over time, a river can shift its course, migrate across the landscape, seek out and exploit any weakness in the rocks beneath it. The underlying geology does not just influence the river, it actively guides it, shaping not only how fast it erodes, but where it flows at all. This is one of the reasons why, looking at a map of rivers, their paths can seem almost deliberate. They do not simply run straight from high ground to low ground. They curve around resistant ridges, follow ancient fault lines, cut through soft valleys while leaving hard plateaus untouched beside them. The river is responding to the land, reading it in a way, finding where the land is willing to give. There is something deeply meditative about this process when you sit with it for a moment. The river does not hurry. It does not plan. It simply moves, following the pull of gravity, doing its work moment by moment. And over time, over the kind of time that makes human history feel like a single breath, it reshapes everything it touches. A cliff face that seems perfectly solid to us might, over 10,000 years, be reduced to rubble by the patient action of water. A valley that seems ancient and permanent was itself carved from flat land, cut slowly downward by a river that is still working, still eroding, still carrying the pieces of the landscape away. We tend to think of the land as fixed and the water as transient. But in geological time, it is almost the other way around. The water is the constant. The land is what changes. And the river, moving quietly through its valley, is the instrument of that change, armed with nothing but motion, time, and the unyielding pull of gravity. There's a particular kind of energy to a young river. Something urgent in it, almost impatient. It does not yet meander or spread. It does not pause to deposit what it carries. It simply drives forward and downward, cutting into the earth with a focus that older, calmer rivers have long since lost. In the upper course of a river, near the source where the land is steep and the gradient is sharp, this energy is at its most concentrated. The water moves fast. It carries significant force. And almost all of that force is directed in a single direction, downward. This is vertical erosion at its most active stage. The river does not yet have the energy to work sideways in any significant way. It carves into its own floor, driving the channel deeper with every passing year. And because it cuts down rather than out, the valley it creates has a very recognizable shape, narrow, steep-sided, and deep. The classic V-shaped valley, familiar from mountain landscapes all over the world, is the direct result of this relentless downward cutting. The slopes on either side of a young river are not carved by the water directly. Rather, as the river deepens its channel, the valley walls become increasingly steep and unstable. Weathering and gravity do their work on those exposed sides. Rock crumbles, soil slips, material falls toward the river and is carried away. The valley grows deeper not only because the river cuts its floor lower, but because the walls above are constantly eroding downward to maintain their angle. It is a collaborative process, the river and the hillside working together, each change in one triggering a response in the other. Walk through an upland river valley and you will often notice something unusual about the way it turns. Rather than following a straight path, the valley seems to wind around corners, and on each side of a bend, a ridge of land juts forward, overlapping with the ridge on the opposite side. These are interlocking spurs, one of the most characteristic landforms of a youthful river valley. They form because a young river, cutting through highland terrain, does not bulldoze its way through hard rock in a straight line. Instead, it finds the easier path, winding around the more resistant sections of bedrock, curving first one way and then another to follow whatever weaknesses the geology offers. As it does this, the ridges of harder rock on either side are left standing, protruding alternately from each bank like the teeth of two combs pushed together. Looking down a valley with interlocking spurs, the view ahead seems to close in, each ridge overlapping the next, until the valley disappears around a corner and the river is lost from sight. There is something quietly beautiful about this. The spurs are not accidental. They are a record of the river's path, a physical map of every deviation, every curve, every decision the water made as it worked its way through the high ground. The harder the rock, the more pronounced the spurs. The more resistant the geology, the more the river had to wend, and the more dramatic the interlocking pattern becomes. Where the riverbed itself becomes uneven, where harder sections of rock protrude above softer ones, or where the gradient suddenly steepens, the water responds with turbulence. It quickens over shallow, rocky sections, breaking into white foam, rushing over ridges and boulders in a way that is both beautiful and energetic. These are rapids, and they are a natural feature of the upper course, where the riverbed has not yet been worn smooth and level. Rapids form wherever the river encounters an irregularity it has not yet had time to erase. A band of particularly hard rock crossing the riverbed will resist erosion longer than the softer rock around it, creating a step or a shelf over which the water tumbles. Over time, the river will work to smooth these differences, grinding down the hard sections, deepening the soft ones, but in a young river, the irregularities are everywhere, and the result is that characteristic churning, rushing, white water character that feels so alive and kinetic. Look more closely at the floor of a fast-moving river and you might notice something remarkable: smooth, circular hollows worn into the solid bedrock, perfectly round, almost as if drilled by some precise tool. These are potholes, and they are one of the most fascinating small-scale features of river erosion. They form through a process of concentrated grinding. When fast-moving water catches a pebble or small stone, it can trap it in a natural depression in the rock and set it spinning, kept in motion by the current, swirling round and round in the same spot. As the stone rotates, it grinds against the rock beneath it like a pestle in a mortar, wearing the hollow deeper and deeper. More pebbles may fall in over time, continuing the work. What begins as a shallow scratch in the bedrock can become, over years and decades, a perfectly cylindrical hole that may be half a meter or more across and nearly as deep. Potholes are evidence of the river's patience. They take a long time to form, each one requiring the sustained circular motion of abrasive material over a vulnerable spot in the rock. And yet they form wherever the conditions allow, in rivers across every continent, at every scale. Some of the largest potholes ever found are enormous, several meters wide and deep, worn into ancient riverbeds that have long since dried. Standing beside one, it is almost impossible not to think about the sheer accumulation of time and motion that produced it. As a river ages, its story changes. What was once a steep, energetic young river gradually carves its valley lower, reducing the gradient, slowing the current. The river begins to lose some of its downward cutting power. But erosion does not stop, it simply shifts direction. In a maturing river, lateral erosion begins to play a more significant role. Rather than driving exclusively downward, the river starts to work sideways, wearing away at its own banks, pushing the edges of its valley outward. The V-shaped valley of the upper course begins to open up. The walls become less steep. The floor widens. Over a very long time, a valley that once was narrow and dramatic can be transformed into something broad and gentle, the evidence of its youthful steepness smoothed away by centuries of gradual widening. This process is slow, but it is continuous. Every time a river cuts into one of its banks, swinging against the outside of a curve, pressing against a spur of land, flowing across softer material, it removes a little more. The valley grows wider by small increments, year after year, century after century, until eventually what was once a confined mountain gorge becomes a broad valley floor. And as the valley widens, something else begins to happen. The river, now slower and less powerful, starts to deposit the material it has been carrying rather than cutting further down. Sediment settles on the valley floor. Fine particles of silt and sand build up over time, layer upon layer, creating a flat, fertile surface on either side of the river channel. This is the beginning of a floodplain, one of the most productive and important landforms that rivers create. Floodplains develop most fully in the lower course, far from the steep gradients of the source, but their origins lie in this gradual process of valley widening that begins in the middle stages of a river's development. As lateral erosion pushes the valley walls further and further apart, and as deposition fills in the floor, the floodplain grows, sometimes stretching for kilometers on either side of the river, flat and even, rich with accumulated sediment from countless floods over thousands of years. There is a certain poetry in the contrast between the upper and lower sections of the same river. In the highlands, the river is young and vigorous, carving narrow valleys between interlocking spurs, rushing over rapids, drilling potholes into the bedrock, filled with sound and movement and energy. And then, many kilometers downstream, that same river spreads out across a wide, quiet plain, slowing almost to stillness in places, depositing its load gently onto the land it passes through. The same water that carved a V-shaped valley in the mountains is now building a floodplain in the lowlands. The same force of erosion that once drove relentlessly downward is now, gently, constructing new land. A river's life is a study in transformation, not just of the landscape around it, but of itself. It changes its own behavior as it changes the land. The two are inseparable. The river shapes the valley, and the valley shapes the river, and the process continues, generation after generation of water flowing through a landscape that is never, even for a moment, truly still. Some landscapes stop you completely. Not because they are pretty in a gentle way, but because they are so vast, so sheer, so far beyond ordinary scale, that the mind struggles to take them in all at once. A canyon seen for the first time is one of those experiences. The ground simply ends, and below, far, far below, a river moves, thin as a thread, through a world that spent millions of years carving out of solid rock. It is difficult to look at something like that and fully believe that water did it. water, and time, and the slow accumulation of force applied in the same direction, day after day, for longer than the human mind can genuinely hold. But that is exactly what happened. And the story of how it begins is more intimate than the scale of the result might suggest. Riverbeds are not uniform. They are made of different types of rock laid down at different times, in different conditions, with different compositions. Some of that rock is hard, resistant to erosion, dense, unyielding. Some is soft, clay, certain sandstones, weakly cemented sediment that gives way relatively easily under the pressure of moving water. And when a river flows over a boundary between these two types, something significant happens. The softer rock erodes faster. The harder rock holds. And where they meet at the surface of the riverbed, a step begins to form, a difference in level between the resistant rock and the ground being worn away below it. Over time, that step grows. Water begins to flow over it with increasing force, dropping from the harder layer down onto the softer ground below. And eventually, that step becomes a waterfall. This is one of the most common ways waterfalls are born, not through any dramatic event, but through the quiet, differential work of erosion acting on rocks of unequal hardness. The harder layer forms a cap, a shelf, a lip over which the river pours. And the process, once started, tends to accelerate. At the base of a waterfall, the falling water strikes the riverbed with considerable force. It churns and swirls, creating turbulence that attacks the soft rock below with particular intensity. Hydraulic action, abrasion, the spinning of carried sediment, all of these processes concentrate at the plunge pool, the deep hollow that forms directly beneath the falling water. This pool deepens and widens as erosion continues. But more importantly, the undercutting action of the water begins to eat away at the softer rock beneath the hard cap layer, slowly hollowing out the face of the waterfall from behind. As this hollow grows, the hard cap rock above it becomes increasingly unsupported. It overhangs further and further over empty space. And eventually, in a moment that might come after decades or centuries of preparation, it collapses. A section of the hard cap breaks away and falls, and the waterfall steps back. Its position has moved slightly upstream. The hard lip is now a little further back from where it was before. This process of retreat is one of the most important mechanisms in river geomorphology. A waterfall does not stay in one place. It migrates slowly, episodically, moving upstream over time as the cap rock repeatedly undercuts and collapses. And the evidence of every position the waterfall has ever occupied is left behind in the landscape in the form of a gorge. As the waterfall retreats upstream, it leaves in its wake a steep-sided valley, a gorge, carved into the rock through which it has passed. The gorge records the waterfall's entire history of movement, every position it has ever held preserved in the shape of the rock. Walk downstream from an active waterfall and you are walking through time, through every stage of the waterfall's retreat, through centuries or millennia of geological history written in stone. Gorges are among the most dramatic features that rivers create. Their walls can be nearly vertical, dropping tens or even hundreds of meters to the river below. The rock faces are often exposed and raw-looking, unweathered compared to the gentler slopes of ordinary valleys, because the gorge itself is geologically young, recently carved, in geological terms, and the walls have not yet had time to soften and erode into more gradual slopes. Not all waterfalls form through differential erosion alone. Sometimes a waterfall is created more suddenly, through changes in the land itself rather than the gradual wearing away of soft rock. Earth movements, faults, uplift, the tilting of land along tectonic boundaries, can create sudden steps in a river's profile, places where the gradient changes abruptly and the river is forced to fall. Changes in sea level can have a similar effect. When sea level drops, the river's base level, the point toward which it is eroding, is suddenly lowered, and the river responds by cutting more aggressively downward, often forming a steep section or waterfall at the point where the adjustment begins and working upstream from there. These are called nick points, breaks in the smooth long profile of a river, and they mark places where the river is responding to some change in the conditions it flows through. A nick point is, in a sense, a message written in the landscape, or record of some past event, a tectonic shift, a glacial change, a transformation in sea level, that altered the river's relationship with the land beneath it. Where a river cuts through particularly resistant rock, the results can be extraordinary. Given enough time, enough velocity, enough sediment to use as a grinding tool, a river can carve through almost anything. The process is slow by human standards, but it is inexorable. Hard rock simply takes longer. The channel deepens meter by meter, century by century, until what was once a flat surface becomes a canyon of breathtaking scale. The great canyons of the world are the products of this process taken to its ultimate conclusion. In each case, the essential ingredients were the same: a river carrying significant sediment, flowing over resistant rock, with enough time and consistent conditions for the erosion to accumulate across millions of years. The river does not need exceptional force. It needs persistence. What is remarkable is how variable this process can be, even within a single river system. The same river may erode far more rapidly in one stretch than in another, because of differences in the rock it crosses, differences in the local climate, or differences in how much sediment it is carrying at any given point. A section flowing over soft, fractured rock might deepen its channel many times faster than a section crossing a hard granite ridge a short distance away. The result is a river profile that is uneven, punctuated by changes in gradient, with some sections deep and confined and others still relatively shallow and open. Climate plays a powerful role too. In wetter regions, where rivers carry more water and more energy, erosion is more vigorous. In drier climates, rivers may only run at full power during seasonal floods, spending much of the year as a fraction of their maximum flow. But even intermittent rivers erode. Even seasonal floods carve. Given geological time, even a river that runs for only part of the year can produce landscapes of extraordinary drama. Human involvement has changed the story in many places. Rivers today are dammed, diverted, channeled, and managed in ways that alter their natural behavior profoundly. Dams trap sediment that would otherwise travel downstream, reducing the river's capacity to erode and deposit. Artificial channels straighten rivers that would naturally meander, changing the way water moves through the landscape. The banks are reinforced, the floodplains built upon, the natural process is constrained. And yet, even heavily managed rivers continue to erode. They press against their banks. They scour beneath their beds. They find weaknesses in the structures built to contain them. A river cannot be entirely stopped, only redirected, slowed, or temporarily held. The forces that have been shaping river landscapes for hundreds of millions of years do not simply cease because a concrete wall has been built. They adapt, and they continue. This is perhaps one of the most humbling things about rivers, the reminder that geological processes operate on timescales and at scales of energy that make human engineering feel provisional. We can manage rivers for decades, even centuries. But the river's own timescale is measured in millions of years, and on that timescale, human interventions are brief interruptions at most. The canyons and gorges that rivers have already carved are monuments to this patience. Each one is the result of a process so slow as to be imperceptible from year to year, yet so consistent over geological time that it has reshaped entire continents. A canyon that took 5 million years to form was, in a sense, carved one grain of sand at a time. Stand at the edge of a deep gorge, look down at the river still moving at the bottom, still cutting, still working, and you are looking at a process that has no end in sight. The river is not finished. It was never finished. It is doing now exactly what it has always done, finding the weak points, carrying the load, grinding against the rock beneath it with every particle it carries, every hour of every day. The landscape you see is not a finished thing. It is a moment captured in an ongoing process, the latest frame in a film that has been running since long before there were any eyes to watch it. Pick up a handful of sand from a beach and hold it for a moment. Each grain has a history. It did not simply appear at the shore. It was once part of something else, a cliff face, a boulder, or rocky hillside somewhere inland, perhaps far inland, perhaps in mountains you will never visit. It was broken loose by weathering, carried into a stream, passed from stream to river, transported across a landscape over years or decades or centuries, and eventually delivered here, to the coast, where it came to rest. Rivers are the great carriers of the earth. They connect the high places to the low ones, the mountains to the sea, the interior of continents to their edges. And the material they carry, the sediment, the silt, the sand, the dissolved minerals, represents the slow dismantling of the land itself. Grain by grain, particle by particle, moved steadily toward the ocean over geological time. This process of transportation is central to everything rivers do. Erosion may be the more dramatic part of the story, the part that carves canyons and deepens gorges. But transportation is what connects all the stages of a river's journey. What links the upper course to the lower course, what binds mountain landscapes to coastal ones. Without transportation, the material eroded from the highlands would simply pile up nearby. It is the river's carrying capacity that distributes it across the landscape, and ultimately into the sea. Rivers carry their load in several different ways, and the method depends on the size and weight of the material being moved. The finest material, very small particles of silt and clay, travels in suspension, held up within the water column by the turbulence of the current. You can see this when a river runs brown or gray after heavy rain. The color is the sediment, so fine that it does not sink, kept aloft by the movement of the water. These suspended particles can travel extraordinary distances, carried along for as long as the river maintains sufficient velocity to keep them from settling. Only when the water slows significantly, or spreads out, do they finally begin to drift downward. Slightly larger and heavier material, sand grains, small pebbles, moves in a completely different way. These particles travel by saltation, a word that describes a characteristic bouncing or leaping motion. A grain of sand caught by the current is lifted briefly from the riverbed, carried forward a short distance, and then drops back down. The impact with the bed may disturb other grains, setting them in motion in turn. And so the process continues, a rolling, hopping, intermittent migration of particles along the riverbed, each one making short jumps downstream before settling again temporarily. The largest and heaviest material, boulders, cobbles, coarse gravel, moves by traction. These pieces are too heavy to be lifted into the water column, too large to bounce. Instead, they are dragged along the riverbed by the force of the current, rolling and sliding slowly forward. Traction requires considerable energy. Only a fast, powerful river with high discharge can move large boulders by traction. In gentler, slower sections, these heavy pieces come to rest and stay there until conditions change. Together, suspension, saltation, and traction account for the full range of a river's carrying capacity. A river in flood is moving material by all three methods simultaneously: large boulders grinding along the bed, sand grains bouncing above them, fine silt swirling in suspension overhead. It is a complex, layered system of movement, operating at different scales at the same time. And the amount of material a river carries can change dramatically with conditions. During normal, low-flow periods, a river may carry relatively little sediment. The water is clear or only faintly clouded. The bed is visible. But when a storm hits the catchment, when heavy rain falls across the basin and water pours into every tributary at once, the river transforms. Flow increases rapidly, velocity rises, and the energy available for sediment transport multiplies. Suddenly the river is carrying many times its normal sediment load, tearing material from its banks, picking up particles it could not have moved the day before, running dark and turbid with suspended material. These high-flow events, though they may last only hours or days, do a disproportionate amount of the river's total sediment transport work. A single major flood can move more material than years of normal flow combined. The river's long-term landscape shaping power is therefore not evenly distributed across time. It is concentrated in these episodic moments of high energy, when the river briefly operates far beyond its everyday capacity. This connects rivers to something much larger than the landscape they immediately occupy. Rivers are part of a planetary system of material transport, a slow, ongoing movement of matter from the highest elevations of the continents to the floors of the oceans. The sediment a river carries is not just rock and sand. It includes organic material, fragments of leaves, woody debris, soil particles rich with carbon compounds. When rivers carry this organic material to the sea, they are participating in the global carbon cycle, transferring carbon from the land to the ocean, where it may eventually be buried in marine sediment and locked away for millions of years. This is not a trivial contribution. Rivers are significant pathways in the Earth's carbon budget, connecting terrestrial ecosystems to marine ones, influencing the concentration of carbon dioxide in the atmosphere over geological timescales. The river does not just shape the land. It participates, quietly and continuously, in the regulation of the planet's climate. Rivers also carry nutrients, phosphorus, nitrogen, dissolved minerals leached from soils and rocks upstream. These nutrients feed the ecosystems through which the river passes and the ecosystems at the river's mouth, where the nutrient-rich water meets the sea. The extraordinary biological productivity of river deltas and estuaries is in large part a consequence of this nutrient transport, the river delivering, at its final stage, the accumulated chemical wealth of an entire watershed. In this sense, rivers are ecological as well as geological agents. They do not just move rock. They move life. The nutrients that feed a delta fishery began as minerals in a mountainside soil, dissolved by rainwater, transported downstream through hundreds of kilometers of river channel, delivered finally to a coastal wetland where they support an entire food web. The mountain and the delta are connected by the river into a single functioning system. And then there is the sorting. One of the most elegant aspects of river sediment transport is the way rivers naturally organize the material they carry by size and weight as they slow down. In the steep, fast upper course, the river can carry everything: boulders, gravel, sand, silt, all moving together in the powerful current. But as the gradient decreases and the river slows, it begins to lose carrying capacity. The heaviest particles, which require the most energy to keep moving, are the first to be deposited. Boulders come to rest in the upper reaches. Coarse gravel settles out as the river slows further. Sand is deposited in the middle course. And the finest silt and clay, which need almost no energy to remain suspended, travel the furthest, settling only when the river reaches the near stillness of its mouth or spreads across a floodplain. This graded sorting is not random. It is a physical inevitability, the direct consequence of the relationship between particle size and the energy needed to transport it. The result is that river sediments follow a predictable pattern across the landscape. Walk from the mountains to the coast along a river's path and the sediment beneath your feet changes gradually, from coarse and angular near the source to fine and smooth near the sea. The river has sorted its cargo as it traveled, delivering each grade of material to the place where the river's energy is just sufficient to carry it, and no further. Fine sediment carried in suspension has a particular relationship with floodplains. When a river overtops its banks and spreads across the flat land beside it, the water suddenly has a vast area to cover and slows dramatically. The suspended silt and clay settle out of this slow, shallow water, draping the floodplain in a thin layer of fine material. This happens again with the next flood, and the next. Over centuries, the accumulated layers build up into the deep, rich soils that make floodplains among the most fertile agricultural land on Earth. The river has not just shaped the landscape, it has built the very foundation of some of the world's most productive farmland, deposited grain by grain with each passing flood. There is something profoundly orderly about all of this when seen from a distance. The river takes material from where it is abundant, the eroding highlands, and delivers it to where conditions allow it to rest, the plains and the sea. It sorts as it goes, organizes as it deposits, builds new landforms from the very material it has dismantled elsewhere. The mountain is slowly carried to the coast. The highland is gradually lowered, and the lowland is gradually raised. Given enough time, a river system tends toward a kind of equilibrium, a balance between erosion and deposition, between the energy available and the work being done. It never quite reaches that equilibrium, because conditions are always changing, rainfall patterns shift, sea levels rise and fall, the land itself moves. But the tendency is always there, always pulling the system toward balance, the river adjusting and readjusting, carrying a little more here, depositing a little more there, always in response to the forces acting upon it. A river carrying the mountains away is not destroying the world. It is redistributing it. Moving the material of the earth from one place to another, building new landscapes from the ruins of old ones, connecting every part of the land surface into a single slow-moving system of transformation. And through it all, the water moves. Unaware of any of this. Simply following gravity, doing what water has always done, carrying with it the quiet, patient work of a planet remaking itself. A perfectly straight river is, in nature, almost a contradiction. Given enough space and time, a river will always curve. It cannot help itself. The physics of moving water, the subtle irregularities of the landscape, even the rotation of the earth itself, all of these things conspire to pull a river away from a straight path and into the graceful, looping curves that we recognize as one of the most distinctive signatures of a mature river system. Meanders are not a sign of a river wandering aimlessly. They are not imperfections, or failures to find the most efficient route. They are a natural and almost inevitable consequence of how water moves through a channel, and understanding them reveals something genuinely beautiful about the physics of flowing water. It begins with a simple fact. Water moving through a channel does not all travel at the same speed. The water near the banks and the bed is slowed by friction, the drag of the solid surface against the moving fluid. But the water toward the center of the channel, away from those frictional surfaces, moves faster. And this difference in velocity across the channel is the seed from which every meander grows. In a perfectly straight channel, something that almost never exists in nature for long, this velocity difference is relatively symmetrical. But any slight irregularity in the riverbed, any small difference in the hardness of the bank material, any minor obstruction, will cause the fastest thread of water to shift slightly to one side. When that happens, the faster water begins to press more strongly against one bank. Erosion on that side increases. The bank yields slightly, and the channel begins to curve. And here's where the process becomes self-reinforcing. Once a slight curve exists, the dynamics of the water change in ways that make the curve grow larger rather than smaller. In a curved channel, the water does not simply follow the bend passively. Instead, it develops a complex three-dimensional movement, a spiraling, corkscrew pattern known as helicoidal flow. As the water swings around a bend, centrifugal force pushes it toward the outer edge of the curve. The water surface is actually slightly higher on the outside of the bend than the inside, a small but measurable difference. This creates a pressure gradient that drives water along the surface toward the outer bank, and simultaneously pushes water along the bed back toward the inner bank, completing a continuous spiral motion within the channel. This helicoidal flow is not merely a curiosity. It is the engine of meander development. The surface flow carries energy outward, directing erosive force toward the outer bank. The return flow along the bed carries sediment inward, depositing it on the inner bank. The two processes work in opposite directions simultaneously, and together they produce exactly the asymmetry that makes a meander grow. On the outside of the bend, the water moves faster and with more force. It strikes the bank at an angle, pressing against it, undermining it from below, removing material with a combination of hydraulic action and abrasion. The bank is cut back. It steepens. In many cases, it develops into what is called a river cliff, a near-vertical face of exposed soil and rock where the bank has been undercut by the current and has collapsed, or is in the process of collapsing. River cliffs can be modest features, a meter or two high, in a small lowland river. In larger rivers, they can be considerably more dramatic, steep exposed faces of layered sediment that reveal the geological history of the floodplain and cross-section. The undercutting that produces these cliffs is a process worth dwelling on. The fastest water near the outer bank flows not just against the bank face, but beneath it, eroding the base of the bank while the material above is temporarily left unsupported. The bank overhangs slightly. Roots of riverside trees may be left dangling in open air. And then, sooner or later, the weight of the unsupported material above exceeds what the remaining base can hold, and a section collapses, falling into the river, where it is broken up and carried away, exposing the fresh bank face behind it to the same process all over again. On the inside of the bend, everything is different. Here the water is slower, the energy is lower, and the helicoidal return flow is depositing the sediment it has swept along the bed from the outer bank. This sediment accumulates in a low, gently sloping mound of sand and gravel that builds up over time, growing slightly with each passing flood. This is the point bar, one of the most recognizable features of a meandering river. Point bars have a characteristic shape. They are highest where they meet the inner bank and slope gently down toward the water's edge. Their surface may be ribbed with low ridges and swales, the signatures of successive depositional events, each slight addition to the bar preserved in the gentle topography of its surface. Looking at a well-developed point bar from above, you can sometimes read the history of the meander's growth in those curved ridges, each one a former position of the inner bank, each one a record of how far the bend had developed at a particular moment in the past. As the outer bank retreats through erosion and the inner bank advances through deposition, the meander bend migrates. The curve moves, not randomly, but in a consistent direction, the outside eroding, the inside building, the whole bend slowly shifting downstream and growing more pronounced. What began as a gentle curve becomes a broad loop. The neck of land enclosed within the loop narrows as the meander grows more extreme. And the river channel becomes longer and longer as the meanders develop, even though the actual distance between the river's source and its mouth across the landscape remains the same. This lengthening of the channel is one of the interesting consequences of meander development. A straight channel of 10 kilometers might become, through meandering, a river channel of 20 or even 30 kilometers, winding back and forth across a valley floor several times before reaching the same endpoint. The river has made itself longer in order to accommodate the energy it carries, spreading that energy across a greater length of channel, reducing its gradient, adjusting to the relatively flat terrain across which it flows. Meanders develop most vigorously across flat land, where the river has the freedom to swing sideways without immediately encountering resistant rock or steep valley walls. In the middle and lower courses, where the floodplain is broad and the gradient gentle, the river has room to develop fully, and the soil and alluvial material of the floodplain is far more easily eroded than the hard rock of the upper course, making lateral migration easier. The width of the valley floor, the character of the bank material, the discharge of the river, the amount of sediment it carries, all of these factors influence how meanders develop and how large they grow. A river carrying a heavy load of coarse sediment tends to form different patterns from one carrying mainly fine material. A river with highly variable discharge, low for much of the year but briefly very high during floods, meanders differently from one with a more consistent flow. But despite all this variation, the underlying process is the same everywhere. Differential velocity across the channel. Helicoidal flow developing in the bends. Outer bank erosion and inner bank deposition, feeding each other, amplifying the curve, driving the meander to grow larger and more pronounced until something, a resistant patch of rock, a valley wall, some other constraint, finally limits how far the bend can develop. Watching a meandering river from above, from a hill, or from an aerial photograph, is one of those experiences that quietly demonstrates the elegance of natural processes. The curves are never quite identical. Each meander has its own character, its own asymmetry, its own particular stage of development. And yet there is an unmistakable family resemblance, a coherence to the pattern that speaks to the underlying physical laws producing it. The river is not choosing its path. It is not deciding where to erode or where to deposit. It is simply responding, moment by moment, to the forces acting on it. And yet the result is a landscape of extraordinary grace, looping curves of blue water across green floodplains, each bend a record of the same simple physics, played out over and over again across 1,000 different rivers on every continent on Earth. There is something almost restful in that. In the knowledge that the curves of a river are not random, not chaotic, but the product of laws so consistent and so fundamental that the same pattern appears wherever the conditions allow. The river meanders because it must. And in doing so, it creates some of the most quietly beautiful landforms the world has to offer. A river seen from above tells a different story than a river seen from the bank. From the bank, it seems fixed, a permanent feature of the landscape, as settled and certain as the hills around it. But from above, from a height that lets you see the full sweep of the valley floor, a different truth becomes visible. The floodplain is marked with curves. Not just the curves of the river as it flows today, but older curves, ghost curves, traces of channels that once carried the same water through slightly different paths. Pale arcs in the grass, subtle depressions in the flat land, the faint outlines of loops and bends that the river has long since abandoned. The valley floor is not just the river's current home. It is a record of everywhere the river has ever been. Rivers wander. Not quickly, not dramatically, but persistently and inevitably, across timescales that a human lifetime is too short to witness fully. A river channel that sits in one position today will, given centuries, have shifted considerably, eroding one bank, depositing on another, migrating sideways across its floodplain in a slow, continuous reworking of the landscape. This channel migration is a direct extension of the meander process. As the outer banks of bends erode and the inner banks build up with deposited sediment, the entire meander moves. It sweeps downstream, it shifts laterally, it grows more pronounced. And as it moves, it leaves behind it a floodplain that has been reworked, composed almost entirely of material that has at some point passed through the river channel, been deposited, reworked again, deposited again, in a cycle of perpetual redistribution. The floodplain is not, therefore, a passive recipient of whatever the river happens to deposit on it. It is more accurate to think of it as material that the river is constantly cycling through, picking up from one bank, carrying downstream, laying down somewhere else. The river does not merely sit on the floodplain. In a very real sense, it is the floodplain, having built almost every part of it through its own past activity. As meanders grow larger and migrate, the loops they form become increasingly exaggerated. A bend that begins as a gentle curve can develop, over time, into an almost complete circle, a great loop of river that nearly doubles back on itself, with only a narrow neck of land separating the two sides of the channel. These extreme meanders are among the most visually striking features of mature river systems, their loops visible from a great distance, the river tracing an elaborate signature across the flat land of its floodplain. But extreme meanders carry within them the seed of their own transformation. As the loop grows tighter and the neck of land between the two channel sides becomes narrower, the river approaches a threshold. During normal flow, the water continues to follow the full length of the loop. But during a flood, when the river is running high and fast and carrying far more energy than usual, it may find a more direct path. The floodwater spreads across the narrow neck of land, and if it is able to erode through, the river suddenly has a new, shorter route. This is called a meander cutoff, and it can happen with remarkable speed. A loop that took centuries to develop can be bypassed in a matter of hours during a single flood event. The water finds the shorter path, the new channel rapidly deepens as all the river's flow is directed through it, and the old loop, that great curve of river that so recently carried the full flow, is suddenly isolated. For a time, the abandoned loop still holds water. It becomes an oxbow lake, a curved, crescent-shaped body of still water, separated from the main channel, no longer part of the flowing river system. The shape is distinctive and immediately recognizable, a smooth arc of water, closed at both ends, reflecting the sky from the flat land of the floodplain. The name comes from the U-shaped wooden frame once used around the neck of an ox. The resemblance is apt. Oxbow lakes are quiet places. Cut off from the river's current, the water becomes still. Sediment settles. Aquatic vegetation takes hold. the ecology of the lake develops along different lines from the river that created it, slower, more stable, more stratified. What was once a rushing bend in an active river becomes a calm, enclosed world of reeds and still water, its curved shape the only visible reminder of what it once was. But oxbow lakes do not last forever. Cut off from the river's flow, they receive no fresh sediment input and are no longer scoured clean by the current. Gradually, they fill. Sediment washed in by rain, organic material from the vegetation growing in and around them, material deposited during occasional floods when the river briefly reconnects with the lake, all of this accumulates, slowly raising the bed of the lake, reducing its depth. Over decades and centuries, an oxbow lake becomes shallower, then marshy, then a wet depression in the floodplain, and eventually, if enough time passes without flooding, simply a slightly lower, slightly damper section of floodplain grass, its curved outlines still faintly visible in the topography but no longer holding open water. These remnants are called oxbow scars, the last traces of a lake that was itself the last trace of a meander that once carried a full river. They are among the most layered pieces of landscape history you can find, each one a compressed record of change spanning thousands of years, written in the subtle contours of a floodplain that most people would walk across without noticing. The river, meanwhile, has moved on. Its new, straighter channel carries the flow efficiently for a time. But the same physics that created the old meander will, inevitably, begin to create new ones. A slight irregularity, a difference in bank material, a subtle shift in velocity across the channel, and the process begins again. New bends develop. They grow. They migrate. Eventually, perhaps thousands of years from now, new oxbow lakes will form from these new meanders, and the floodplain will accumulate new scars to layer over the old ones. This migration of river channels across floodplains is not merely a matter of geological interest. It has very real consequences for the landscapes and ecosystems alongside rivers, and for the people who live among them. Bank erosion, the same process that drives meander development and channel migration, can be a significant hazard. A riverbank that has been stable for decades may, if the river's course shifts slightly or if an unusually powerful flood increases erosive energy, begin to retreat rapidly. Meters of bank can be lost in a single flood season. Land that was productive farmland, or that supported buildings or roads, can be undermined and lost to the river. In this sense, the river's slow reshaping of its landscape is not simply a background geological process, it is an active force that intersects with human land use in ways that can be costly and sometimes dangerous. Flood events amplify this considerably. When a river overtops its banks and spreads across its floodplain, it does not flow gently over the flat land. The water moves, it carries sediment, it erodes softer material from the floodplain surface, and it deposits elsewhere. A major flood can significantly rework the surface of a floodplain in a matter of days, cutting new channels, filling old ones, shifting banks, depositing sediment ridges. The landscape after a large flood may look noticeably different from the landscape before it. And yet, for all the hazard that bank erosion and channel migration can represent in human terms, these same processes are essential for the ecological health of river systems. A river that is allowed to migrate, to erode its banks, to create oxbow lakes, to build point bars, to abandon old channels, creates an extraordinarily rich mosaic of habitats. The main channel provides fast-flowing, well-oxygenated water for species adapted to current. The point bars offer shallow, warm, sandy areas where certain fish spawn and invertebrates thrive. The outer bank cliffs, with their exposed faces and overhanging roots, provide nesting sites for kingfishers and sand martins. The oxbow lakes offer calm, still water habitats for species that cannot survive in fast currents, different plants, different invertebrates, different amphibians. The wet, marshy ground around aging oxbows supports yet another community of species, different again from those in the open water. A naturally wandering river, allowed to meander and migrate across its floodplain, is not a single habitat but many, a corridor of ecological diversity created and maintained by the very processes of erosion and deposition that also shape the landforms. The river's restlessness is its productivity. Its wandering is what makes it rich. This is one of the reasons why the management of rivers for flood control or navigation, straightening channels, reinforcing banks, preventing the natural migration of meanders, can have significant ecological consequences. When a river is fixed in place, when its banks are held firm by concrete or steel, when its meanders are cut off and it is forced to flow in a straight line, the habitat mosaic it once supported is reduced or destroyed. The diversity that depended on the river's wandering nature disappears, along with the species that required it. There is a growing recognition among river managers and ecologists that the most sustainable approach to river management works with the river's natural tendencies rather than against them, allowing rivers to migrate within defined limits, restoring meanders that were artificially straightened in the past, giving rivers back some of the floodplain they need to function as natural systems. The results, where this has been tried, are often remarkable. Rivers that were ecologically impoverished after decades of engineering recovering their diversity within years of being allowed to meander again. The river, given the chance to wander, knows what to do. It has been doing it for millions of years, long before there were people to straighten it or dam it or reinforce its banks. The oxbow lakes, the point bars, the migrating channels, the scars on the floodplain, these are not problems to be solved. They are the river working as it was always meant to work, shaping a landscape that is alive precisely because it is always, quietly, changing. For as long as people have settled near rivers, they have understood something that took science much longer to explain formally. The land beside a river is different from the land further away. It is darker, deeper, richer. It holds moisture well. It produces abundantly. The farmers of ancient Egypt did not need to understand alluvial geomorphology to know that the black soil left behind by the Nile's annual flood was the source of everything, of the harvest, of the food, of life itself. They knew it in their hands, in the weight of the soil, in the way crops grew tall and full in the flood deposits that the river renewed each year. What they were experiencing, though they described it in the language of gifts and gods, was the geological process of floodplain building, one of the most consequential things a river does, not just for the landscape, but for the human world that has grown up alongside rivers across every inhabited continent. When a river overtops its banks and spills across the flat land on either side, it undergoes an immediate and dramatic change. Within the channel, the water is confined and fast. Spilling out across the open floodplain, it suddenly has an enormous area to spread across, and it slows. That slowing has direct consequences for what the water is carrying. A fast river can hold sediment in suspension, fine particles of silt and clay, kept aloft by the turbulence of the current. But as the floodwater spreads and slows, that turbulence decreases, and the suspended material begins to settle. The finest particles drift downward through the shallow floodwater, gently, almost imperceptibly, and come to rest on the surface of the floodplain. When the flood recedes, when the water drains back into the channel or soaks into the ground, it leaves behind a thin layer of fine sediment, draped evenly across the land like a light dusting of the most fertile material the river has to offer. This happens again with the next flood. And the next. Each inundation adds another thin layer of alluvium, fine-grained, mineral-rich, organic-laced sediment that has been carried from the wider catchment, from soils and hillsides far upstream, and delivered here to the floodplain. Over centuries, these layers accumulate. The floodplain builds up, millimeter by millimeter, flood by flood, into a deep, fertile, remarkably uniform deposit that may extend for kilometers on either side of the river and reach many meters in depth. The fertility of these alluvial soils is not accidental. The sediment that a river carries downstream has been weathered from rock, enriched by organic material, mixed with nutrients leached from a vast catchment area. It represents, in a sense, the concentrated goodness of an entire landscape, gathered by the river from its source to its mouth and spread generously across the floodplain with each flood. The river is not just shaping the land. It is feeding it. But not all of the sediment carried by a flooding river travels far from the channel. The heaviest material, coarser sand and fine gravel, settles out almost immediately when the water leaves the channel, piling up close to the bank. Over repeated floods, these coarser deposits build up into a raised ridge running parallel to the river on both sides. This is a natural levee, and it is one of the most important small-scale landforms that rivers create. Natural levees are subtle features, often only a meter or two above the general level of the floodplain, but their effects on the surrounding landscape are significant. They form a slightly elevated ridge along the river's edge, higher than the land further away from the channel. This means that the floodplain behind the levee, the land further from the river, is actually lower than the land immediately beside it, trapped in a shallow basin between the levee and the valley wall or the next tributary. These low-lying areas behind levees are called back swamps. They are among the wetter, quieter corners of a floodplain, places where floodwater that has spread across the plain and deposited its sediment on the levee and the near floodplain cannot easily drain back to the river. The water collects in these shallow basins and drains away slowly, if at all. Back swamps tend to be poorly drained, seasonally flooded, and characterized by waterlogged soils rich in organic material, the accumulated remains of the wetland vegetation that grows there. They are not dramatic landscapes, but they are ecologically important ones. Waterlogged, organic-rich, seasonally flooded, back swamps provide conditions that relatively few other habitats replicate, and the species that depend on those conditions are often highly specialized. certain wetland plants, amphibians, wading birds, and insects find in back swamps the particular combination of water, organic material, and seasonal flooding that they require. The natural levee and the back swamp together form a characteristic pattern repeated along meandering rivers across the world. The slightly elevated, drier, more easily farmed ground close to the river, and the lower, wetter, less accessible ground further away. It is a pattern that is profoundly shaped where people have chosen to settle along rivers, favoring the well-drained levee tops for villages and farmland while leaving the back swamps as wetland or rough pasture. Rivers also slow and spread floodwaters through the physical complexity of the floodplain itself. The irregular surface, ridges of former levees, depressions of old channels, point bar sequences, oxbow lakes, back swamps, creates friction and storage that delays the movement of floodwater across the plain. Water that spreads into this complex terrain moves more slowly and takes longer to drain than it would across a perfectly flat surface. This natural storage and attenuation of floods is one of the important hydrological functions of an intact floodplain, reducing the speed and height of flood peaks downstream. Along the river's course, the material it deposits is not limited to the fine silts of the floodplain. Sand and gravel bars accumulate in the channel itself and on point bars at meander bends. Coarser material is deposited where the river's velocity drops, around obstacles, in the lee of bends, at the junction of tributaries where two currents meet and slow each other. Organic matter, waterlogged wood, leaf litter, plant debris, accumulates in quieter backwaters. All of this material contributes to the texture and fertility of the river corridor, enriching the soils and sediments through which the river moves with a mixture of mineral and organic material that supports the dense, productive vegetation typical of riversides. Near the river's mouth, as it approaches the sea or a lake, the water slows to its gentlest pace. The finest suspended material, the last of the silt and clay that has traveled perhaps hundreds of kilometers from its source, finally settles, accumulating in broad, flat expanses of fine sediment at the water's edge. These are mud flats, some of the most productive and most overlooked environments in the natural world. Mud flats look, at first glance, like nothing much. Flat expanses of gray or brown mud, exposed at low tide, glistening under open sky. Featureless, apparently lifeless. But they are in fact extraordinarily rich in invertebrate life, worms, mollusks, crustaceans, burrowing creatures of all kinds, sustained by the nutrient-rich fine sediment and the organic material it contains. Mud flats are critical feeding grounds for huge numbers of wading birds and wildfowl, for juvenile fish, for species at every level of the food web. Their apparent emptiness is deceptive. Beneath the surface, they are teeming. And mud flats are also the first stage in a longer process of land building. Once fine sediment has begun to accumulate in an area shallow enough for plants to colonize, pioneering salt-tolerant vegetation takes hold. The roots of these plants trap more sediment, binding it in place, stabilizing the surface against the erosive action of waves and currents. As the vegetation spreads and the sediment builds up further, the mud flat gradually becomes a salt marsh or a freshwater wetland, a new piece of land, created by the river's deposition and consolidated by the plants that colonize it. This role of vegetation in stabilizing river deposits is crucial throughout the floodplain and delta system, not just at the coast. Plant roots bind alluvial sediment together, increasing its resistance to erosion, allowing landforms to persist that would otherwise be reworked by the next flood. The willow trees along a riverbank, the reeds in the back swamp, the salt marsh grasses at the tidal limit, all of these are doing more than simply growing. They are holding the land in place, making the river's depositional work permanent rather than temporary. In the oldest, most mature river systems, where the gradient has been reduced to almost nothing and the river has had millions of years to work across its floodplain, the landscape becomes very broad and very smooth. The river moves slowly, carrying mainly fine material, depositing gently, spreading widely. The sharp-edged valleys of the upper course, the dramatic meander loops of the middle course, these are far behind. Here, the river seems almost reluctant to move, meandering so gently across its vast floodplain that the current is barely perceptible. These late-stage river landscapes have a particular quality of stillness. The land is flat, the water is calm, the horizons are wide. There is nothing dramatic here, no waterfalls, no gorges, no rapids. Just the river, unhurried, spreading its final deposits across a landscape it has spent an eternity building. And in that stillness is an enormous quiet productivity. The deep alluvial soils of mature floodplains support some of the world's most fertile agricultural land. The wetlands and back swamps harbor extraordinary biodiversity. The mud flats and coastal wetlands at the river's mouth are among the most ecologically valuable environments on the planet. All of it built, slowly and patiently, by the river depositing what it carried, layer by layer, flood by flood, century by century. The river began in the mountains as energy in motion. It ends here as land, solid, fertile, teeming with life. The journey from source to mouth is, in the end, a journey from erosion to creation, from the carving away of the old to the building of the new. And the floodplain, spread out beneath an open sky, is the record of that journey. Every flood, every deposit, every layer of silt, a page in a story that the river has been writing since long before anyone was there to read it. Every river, no matter how long its journey, no matter how many landscapes it has crossed or reshaped along the way, is moving toward the same destination. The sea. Or a lake, or an inland basin, but most often the sea, that vast final recipient of everything the river has carried since its first moments high on a distant hillside. The approach to the end is gradual. The river does not arrive at the coast suddenly. It eases into it, the gradient flattening further with every kilometer, the current slowing, the channel widening, the landscape opening out on either side. By the time a river reaches its lower course, it has lost most of the energy it once had. The rushing, cutting, turbulent water of the upper reaches is long behind it. What remains is something much quieter, a broad, slow-moving body of water carrying the last of its sediment load toward a final resting place. In the lower course, deposition dominates in a way it has not done anywhere upstream. The river is simply too slow, too gentle, to hold much of what it carries. Sediment that has traveled hundreds of kilometers begins to settle. The river deposits on its own bed, on its banks, across its floodplain, and finally, As it meets the standing water of the sea, it releases the last of its load in a concentrated burst of deposition that can, over time, build entirely new land. The place where a river meets the sea takes two principal forms, and the difference between them comes down to a balance of forces, what the river brings in, and what the sea takes away. In many places, the sea is strong enough to receive and disperse the river's sediment before it can accumulate significantly. Waves and tidal currents sweep material along the coast, prevent it from building up at the river's mouth, and maintain an open, funnel-shaped inlet where fresh water and salt water mix in a dynamic, ever-changing environment. This is an estuary, one of the most ecologically rich and hydrologically complex environments that river systems create. But where the river delivers sediment faster than the sea can remove it, particularly in sheltered coastal settings where waves are weak and tidal ranges are modest, something different happens. The sediment builds. It accumulates at the river's mouth, piling up in shallow water, gradually rising toward the surface. New land forms, pushing out into the sea. The river is forced to split around the obstacle it has created, finding new paths around and through the growing mass of deposited material. And the result, over time, is a delta. Deltas form most readily in calm, shallow seas where the conditions favor accumulation over removal. When waves are gentle and tidal currents are weak, the river's deposits are not constantly reworked and redistributed by marine energy. They stay where the river puts them. And shallow water near the coast means that the sediment does not have far to build before it reaches the surface and becomes land. The geometry of a delta is determined by this competition between river input and marine energy. Where the river is dominant and the sea is calm, deltas tend to be elongated, extending far out to sea along the river's main channel, like outstretched fingers pushing through quiet water. Where wave energy is stronger, deltas tend to be smoother and more arc-shaped, their seaward edge rounded and reworked by wave action into a more regular curve. Where tidal currents dominate, deltas develop a different pattern again, their distributary channels aligned with the tidal flow, the sediment organized by the rhythm of ebb and flood. As a delta grows, the river cannot maintain a single channel across it. The channel becomes increasingly choked with the sediment it is depositing. The gradient across the delta surface becomes almost imperceptibly shallow, and the river begins to split. New channels branch off from the main one. These are distributaries, and unlike tributaries, which flow into a river, distributaries flow out of it, spreading the river's water and sediment across the growing delta surface like the veins of a leaf. Through these distributaries, the river continues its work of deposition, extending the delta outward in multiple directions simultaneously. Some distributaries carry more flow than others. Some are gradually abandoned as sediment builds up within them, forcing the river to find a new path. The pattern of channels across a delta surface is not fixed, it shifts over time, one distributary growing while another silts up, the river constantly rerouting itself across the land it is building. Geologists have described the internal structure of a delta in terms of three distinct layers, reflecting the different environments of deposition across the delta system. The top-set beds are the uppermost layers, the flat-lying sediments deposited on the delta surface itself, on the floodplain and in the channels of the distributary system. Below them, at the seaward edge of the delta, the foreset beds are laid down, coarser material deposited on the steeper slope at the advancing front of the delta, where it is building out into the sea. And below those, extending across the seafloor ahead of the advancing delta, the bottom set beds accumulate, the finest sediment, the last material to settle, drifting furthest from the river mouth before coming to rest in the quietest, deepest water. These three layers preserve a record of the delta's growth. In the sedimentary rocks of ancient deltas, geologists can read this structure and reconstruct the history of river systems that vanished millions of years ago, the direction they flowed, the energy they carried, the conditions of the sea they entered. The delta is not just a landform. It is an archive. One of the most fascinating processes occurring at the meeting point of river and sea is almost invisible, a chemical transformation that happens at the molecular scale, yet has visible consequences for the landscape. In freshwater, fine clay particles carry a slight electrical charge that keeps them repelled from one another, suspended individually in the water column. But when this freshwater meets the salt of the sea, the chemistry changes. The salt ions neutralize the electrical charges on the clay particles, and they begin to clump together, aggregating into larger, heavier masses that sink far more readily than the individual particles would. This process is called flocculation, and it is one of the reasons why deltas and estuaries accumulate such extraordinary amounts of fine sediment so efficiently. The salt water is not just receiving the river's sediment, it is actively helping it settle, triggering a chemical reaction that accelerates deposition and contributes to the building of new land. Not all rivers reach the sea in a single, well-defined channel. In some places, particularly where a river carries a very heavy sediment load and loses energy rapidly, the channel breaks up not into distributaries spreading across a delta, but into a complex network of shallow, interwoven channels separated by bars and islands of deposited sediment. These are braided rivers, and they have a very different appearance from the single-channel meandering rivers of the middle course. Braiding happens when a river is carrying more sediment than its current velocity can transport. As the river slows, whether because the gradient decreases, because it spreads across a wide, flat surface, or because its discharge drops after a flood, it begins to deposit the coarser part of its load on the channel bed. These deposits build up into bars, which divert the flow around them, creating multiple smaller channels on either side. Each of these channels may then deposit its own bars, subdividing further, creating a network of shallow, shifting channels braided together across a wide, gravel-covered floor. Braided rivers are dynamic and unpredictable. Their channels shift constantly, particularly during high flows, when bars are eroded in some places and built up in others. The overall channel pattern can change significantly between one flood season and the next, making braided rivers among the most actively reshaping of all river environments. Walking across the wide, gravelly floor of a braided river during low water, it is almost impossible to imagine which of the many shallow channels will carry the main flow when the next flood comes. The contrast between a braided river and a single-channel meandering river is striking, and it speaks to the enormous variety that river systems display even as they all follow the same underlying physical principles. Both are responding to the same forces: gravity, sediment load, discharge, gradient. but the specific balance of those forces in each case produces radically different forms. And at the sea, all of it comes together. Every grain of sediment that was eroded from a hillside, carried through rapids, abraded in a pothole, deposited on a point bar, reworked by a flood, resuspended and carried further, all of it arrives here, eventually. The river delivers it to the coast, and the coast receives it, and what happens next depends on that ancient balance between what the river brings and what the sea takes away. Where the sea wins, the sediment is dispersed, mixed into marine deposits, spread along the coastline. Where the river wins, land is built, new, flat, fertile land pushing out into shallow water, colonized first by pioneering plants, then by richer vegetation, eventually perhaps by the entire weight of a human civilization drawn, as civilizations so often have been, to the extraordinary fertility of a river delta. The river that began as a trickle on a mountainside has, at its mouth, become a builder of continents. It has carried a piece of the highlands to the sea and set it down as new ground. The mountains are, slowly and perpetually, being carried to the coast, reduced by erosion, transported by water, and deposited at the edge of the sea, where they become something new. That is the river's full story. From the first drop of water finding its way between stones on a high hillside, to the vast, silted, distributary threaded expanse of a delta reaching out into the sea. Every stage connected to every other. Every process a consequence of what came before and a cause of what comes next. The river does not stop. It does not finish. Even where it meets the sea, the work continues, sediment settling, land building, channel shifting, the delta growing imperceptibly outward with each passing year. The river's journey ends, but its effect never does. There is a temptation, when looking at a river valley, to see it as a finished thing. The hills are where they are. The valley has its shape. The river moves through it in its familiar path, and everything seems settled, permanent, established over time and unlikely to change. It is easy to feel, standing beside a calm river on a quiet afternoon, that the landscape around you has simply always been this way. But that stillness is an illusion, and a gentle one. The valley was not always this shape. The river was not always in this position. The hills themselves are lower than they once were. Every feature of the landscape you can see is a temporary state in a process that has been running for far longer than the human mind can easily hold, and will continue running long after every trace of the present moment has been erased. Rivers are not decorative features of the landscape. They are among the primary forces that create it. Over millions of years, not just after floods or storms, not just in dramatic episodes of change, but continuously, in the ordinary daily movement of water through a channel, rivers reshape the surface of the earth with a thoroughness and on a scale that rivals any other geological process. The power of rivers as landscape-forming agents comes from the combination of three things that have been woven through everything in this story: erosion, transportation, deposition. These three processes, working in different proportions at different points along a river's course, are responsible for every landform a river creates, from the V-shaped valley in the mountains to the delta at the coast, from the pothole drilled into a highland riverbed to the deep alluvial plain of a mature lowland river. The balance between these processes at any given point determines the character of the landscape at that point. Where erosion dominates, the land is being worn away. Where deposition dominates, new land is being built. Where transportation dominates, material is being moved from one to the other. And that balance is never fixed. It shifts with every change in discharge, every variation in sediment supply, every alteration in the gradient. A river that is in a state of erosion today might, if conditions change, shift to deposition in the same location. The landscape is always adjusting to the current balance of forces, always responding, always in the process of becoming something slightly different from what it was. This means that even a river that looks calm, that appears to be simply flowing gently through an established valley without doing very much, is still actively reshaping its channel and its banks. The process may be slow. It may be invisible from one year to the next. But it is happening. The outer banks of meanders are being very slightly undercut. The channel bed is being very slightly abraded. Fine sediment is being very slightly redistributed. The river is at work even in its most peaceful moments, and the landscape is, very slowly, responding. Over geological time, this accumulation of small, continuous changes produces transformations of extraordinary magnitude. The same processes that seem negligible in a single human lifetime can, over 1 million years, lower a mountain range by hundreds of meters, carve a canyon 1 kilometer deep, build a delta the size of a small country. The river does not need dramatic force. It needs only consistency in time, and it is both in abundance. The human relationship with rivers has always been close and complicated. Rivers provided water, food, transport, and fertile land. They defined boundaries, powered industries, sustained cities. But they also flooded, eroded, changed course, and defied the attempts of every era to fully control them. The history of human civilization is, in many ways, a history of living alongside rivers and trying, with varying success, to manage the same forces that have been shaping the earth for millions of years. Modern river management has achieved remarkable things. Dams hold back floodwaters, generate electricity, and store water for agriculture and drinking. Channelization, the straightening and deepening of river channels, has allowed floodplains to be farmed and built upon. Levees and flood walls protect cities. These are genuine achievements, and in many cases they have saved lives and supported enormous human populations. But every intervention in a river system carries consequences, and those consequences are often felt far from the point of intervention, and long after the intervention was made. This is because rivers are not isolated channels, they are systems, deeply interconnected across their entire length, and changes made in one part of the system propagate throughout it. Dams are perhaps the clearest example. A dam is extraordinarily effective at trapping sediment. The water impounded behind a dam slows almost to stillness, and the sediment the river was carrying settles out and accumulates in the reservoir. The water released downstream from the dam is therefore sediment-starved, clear of the material it would naturally be carrying. And a river carrying less sediment than its energy would normally support has excess capacity. It compensates by picking up sediment from its own bed and banks downstream, eroding more aggressively than it would in its natural state. The river below a dam can deepen its channel, undercut its banks, and erode structures that were built when the river's sediment load was higher and its erosive behavior was different. Meanwhile, the sediment trapped in the reservoir is no longer being delivered to the lower course in the delta. Deltas that once grew steadily, sustained by the river's sediment supply, begin to shrink when that supply is cut off. Wave erosion, which was previously balanced by deposition, begins to wane. The delta retreats. Coastal land that took thousands of years to build is lost within decades. The consequences of a dam built far inland can be felt at the coast, in the erosion of land that depends on a sediment supply that no longer arrives. The straightening of river channels produces its own cascade of effects. A straight channel has a steeper effective gradient than a meandering one covering the same distance. Because it is shorter, the same drop in elevation is compressed into a smaller length. A steeper gradient means faster water. Faster water means more erosive energy and a greater capacity to transport water quickly through the system. The result is that flood peaks, which a natural meandering channel would have attenuated, spread out and slowed as water traveled through the curves and spread across the floodplain, now pass through the straightened channel faster and arrive downstream with greater height and speed. Flood risk downstream of a straightened channel is typically higher than it was before the straightening, even though the straightening was often done with flood control as one of its stated goals. The river presses against every constraint that human engineering places on it. Reinforced banks are undercut from below. Concrete-lined channels accumulate sediment in their corners. Flood walls are overtopped by events that were not anticipated when they were designed. The river does not stop responding to its own physics simply because a wall has been built beside it. It finds the weaknesses, adjusts to the new conditions, and continues doing what it has always done. This is not a counsel of despair. It is simply a recognition of what rivers are and how they work. A river is not an adversary to be defeated. It is a process to be understood, and the more deeply it is understood, the better equipped anyone, engineer, planner, ecologist, farmer, is to work within its constraints rather than against them. The effects of river processes extend far beyond the channel itself. Sediment eroded from hillsides far upstream shapes the character of a delta hundreds of kilometers away. Nutrients carried by a river from its catchment sustain ecosystems at its mouth that have never been visited by the people whose land contributed those nutrients. Carbon transported by rivers from terrestrial soils influences the chemistry of the ocean and, over geological time, the composition of the atmosphere. A road built too close to an actively migrating riverbank may be undermined within years. A bridge built without accounting for the river's potential to deepen its channel during floods may find its foundations exposed and threatened. Rivers connect everything in a catchment into a single functioning system. The hillslope and the channel. The upland and the lowland. The mountain and the coast. The land and the sea. Changes anywhere in that system send signals throughout it, and the river is the medium through which those signals travel. This is the deepest truth about rivers. Not just that they are powerful, though they are, nor that they are beautiful, though they are, nor even that they have shaped much of the land we live on, though that is also true. the deepest truth is that rivers are connectors. They are the threads that bind landscapes together, that link the processes of mountain erosion to the processes of coastal deposition, that carry the chemistry of inland soils to the biology of coastal seas, that translate the rainfall of a distant watershed into the flood or the drought of a downstream valley. A river is a mountain and a plain and a coast, all moving together through time. It is the hillside and the pothole and the meander and the oxbow and the delta, all part of one continuous story that began long before any human being was there to observe it and will continue long after the last human structures beside it have been reclaimed by the very processes the river has always employed. Sit beside a river for long enough, and you begin to feel this, even without knowing the science. The water moving past you has come from far away and is going somewhere further still. It has worn rock and carried sediment and shaped valleys and built plains. It is older than the channel it currently occupies, older than the valley it flows through, older than the landscape it is still, quietly, in this very moment, reshaping. The river does not begin and it does not end. It is part of a cycle that has been running since water first fell on this planet, evaporating, condensing, falling again, finding its way to the sea, rising once more. It is the Earth's own circulation, its way of moving matter and energy from one place to another, of keeping the surface alive and dynamic and ever-changing. And in that endless movement, in that patient, unhurried, irresistible flow, is perhaps the most restful thing of all, the knowledge that the world is not static, not finished, not fixed. That it is always, in ways too slow to see but too powerful to stop, becoming something new. The river moves. The land changes. And the story, as it always has, continues.